All right, so what we're going to do is look at another problem, and hopefully this will give you an insight how to approach these problems. So question 3 reads, a tractor is being used to pull 2 logs across a field. Okay, a chain connects the logs to each other. The front log is connected to the tractor by a separate chain. The mass of the front log is 180 kilograms, and the mass of the back log is 220 kilograms. The coefficient of friction between the logs and the field is 0.45. The tension in the chain connecting the tractor to the front log is 1850 newtons. Determine the acceleration of the logs and the tension in the chain that connects the 2 logs. So again, the first thing you have to do is draw the free body diagram, okay? So let's see if we can draw that. So we have a tractor. We have a tractor. So this is the tractor. All right, let's do this. All right, so we have a tractor. So this is our tractor here. And you have a chain, and then you have a log. Okay, then you have a chain and another log. Okay. I tell you what, let's draw the tractor a little bit bigger. Okay. So again, the tractor is used to pull 2 logs. Tractor right here. Okay, so log 1, a chain connects each log to each other. So the logs are attached to each other. The mass of the front log, so this is 180 kilograms. Okay, kilogram. And the mass of the back log is 220. So this is 220. So you can see the important thing is to draw the free body diagram. Okay. Now the coefficient of friction is 0.45. The tension in the chain connecting the tension in the chain connecting the front log, the tractor to the front log, is 180. So the tension right here, call it T1. T1 is 1850. Of course, the force is in newtons. And we don't know the tension T2 right down here. We don't know that. Okay? So we don't know that. All right. So again, the tractor is pulling log 1, log 2. There's a chain right there. Okay? Now we can draw the force. Let's look at the force on the system. The force on the system, it is moving forward. So there must be an applied force that the tractor is supplying. So the applied force is gonna go to the right, because say the tractor is moving to the right. Okay, the force moving to the left, is the tension pulling on the tractor trailer going to the left, and T2 pulling this log to the left. Okay, also because the motion is to the right, frictional force is gonna go in the frictional force is gonna be to the left. Okay, so the force is acting on. First of all, let's just look at the force acting on the system as a whole. Okay, so the tension which is 1850, that is what that is the force between the tractor trailer and the log that's 180. Okay, the frictional force. So what we need to do is just what we have to do is just look at just this portion of the system. Okay, look at just this portion. They didn't give you the weight of the tractor trailer, so but that's irrelevant. If you just look at the logs, so call this log 1 and log 2. Log 1 and log 2 is being pulled by the tractor trailer. So the net force pulling log 1 and log 2 is this 1850. Sorry, the force pulling it to the right is 1850. The net force pulling it is going to be 1850 minus the friction. So what we're going to do is just separate out these. So we have log 1 connected to log 2, and the tension which is pulling it, they told us that's 1850. So T1, and T1 is to the right, but going to the left is going to be the frictional force. Going to the left is a frictional force. Okay? All right, so if we just take out the logs, we know that the force pulling the log, which is the tension, okay, is going to the right. The force that's going to pull the log backwards is the frictional force. And it is the frictional force for the system. Remember, the force of friction is equal to the coefficient of friction, mu. In this case, it's 0.45 times the normal force. Okay, we are on a flat surface, so the normal force is equal to the force of gravity. So when you add these two, you get 400. So that's the mass. So the force of gravity is the mass times acceleration. So it's 400. Let's use 10 as the force of gravity for simplicity. Okay, so this is the force of frictional force. So this would be 4.5 times, so 4.5 times 400. So let's see what that is. So 4.5 times 400, that's equal to 1800. So the frictional force is 1800. I mean, it's very high because I guess you're pulling it on a rough surface. You're pulling the logs on a rough surface. So the tension going forward is 1850. The frictional force going to the left is 1800. So the net force, which is the tension minus the frictional force, is, so the net force net, and because the log is moving to the right, so the net force is to the right. So the net force is the 1850 tension minus the friction force. So the net force is 50, right? So the net force is 50 newtons. So this net force going this way is going to cause the system to accelerate. And again, so remember Newton's second law again, the net force is equal to the mass of the system times the acceleration. So again, the mass of the system combined is 400. So 400 times the acceleration is equal to 50. Remember, the net force is 50. So we can solve the equation for acceleration. Therefore, acceleration is equal to 50 divided by 400. So 50 divided by 400. And that is equal to 0.125. So it has a very small acceleration because, you know, you're pulling this thing on the ground. So the acceleration of the system is 0.125 meters per second squared. Meter per second squared. Meter per second squared. Okay? Or meter per second per second. So this is the acceleration of the system. Now they ask you to find the tension between these two logs. So if you just take this system by itself, okay, or just take the backlog. If you take the backlog, the force that's going to act on the backlog is going to be the frictional force going to the left, right? So if you take the backlog, the frictional force going to the left, and then the tension T2 pulling it forward. Okay? So those are the two forces acting on the backlog. Tension, so remember, the tension that developed in this is going to pull it forward. and the frictional force is going to pull it backwards. So the net force acting on the backlog, the net force, is going to be T2 minus the frictional force. The frictional force that's the backlog is going to experience, call that frictional force 0. So this is a frictional force for the backlog now. That is equal to the coefficient of friction. We know that's 0.45 times the normal force. The normal force for the backlog is the normal force is the same thing as the force of gravity, and the force of gravity is the mass times acceleration. So it's going to be 220. That's the mass of the backlog times the acceleration due to gravity, and we round it off to 10. So the force of friction on the backlog is that's going to be 4.5 times 220. So let's see what that is. So that is 4.5 times 220, and that is equal to 990. So the force of friction pulling the log to the left, okay? So the force of friction pulling the backlog to the left is 900. We don't know the tension going forward. That's what we want to calculate. But what we know is that the net force causing the backlog to go forward, that net force is equal to the tension minus friction, right? So it's equal to, we call it, this tension was T2. So it is tension T2 minus the force of friction going to the left, and we know that the force of friction is 900. So T2 minus 900, so that's equal to the net force acting on the backlog. From Newton's second law, we know that net force is the mass, and the mass of the backlog is 220. Mass times acceleration. And remember, we calculate the acceleration for the system. So whatever acceleration the tractor has, the front log is going to have, and the back log is going to have, because they're joined together, so they're going to have the same acceleration. So that's the mass times the acceleration. That is 0.125. That's the acceleration. Okay, so if you're going to solve for T2, so remember, T2 is the tension right here, okay, which is pulling this backlog forward. So T2 is there going to the right, and frictional force going to the left. So the net force, which is the tension minus the frictional force, is equal to the mass times acceleration. So T2, we're solving for T2. T2 is equal to 220 times, let's just work that out so we don't have that. So 220 times 0.125, that is equal to 27.5. So it would be 220 times 1 is 20. Let's round it off to 28. That's 28 And then when you take this over to that side, it's plus 900. So when you add them, it's 928. So the tension in the, so that's Newton, and remember, force is in Newton. So the tension in the back chain or back cable is 928. Okay? All right, so again, it's all Newton's second law. Okay? To get the frictional force is the coefficient of friction times the normal weight. To get the weight due to gravity, or get the force due to gravity, is mass times acceleration due to gravity. Once you have a net force in the system, you'll get an acceleration, and the net force is equal to the mass times acceleration. Okay, so let's move on. So, and you have to do the problems in order to fully appreciate what goes on. All right, so let's look at another problem. So two boxes are held together by a strong wire and attached to the ceiling of an elevator by a second wire. The mass of the top box is 14.2 kilograms. The mass of the bottom box is 10.4 kilograms. The elevator accelerates upwards at 2.84 meters per second. Assume that the wire is relatively massless. All right, so it's the ceiling of the elevator. Okay, you have a wire which attached to this box, which is 14.2 kilograms. Then there's another wire attached to the bottom box, which is 10.4 kilograms. And the elevator is accelerating upwards at 2.8 meters per second squared. They want you to find the tension in the top wire connecting A and B, and then find the tension in the bottom wire. All right, so again, the same thing. You have to look at the forces acting. So the system is moving upwards, okay? So therefore you have to have a net force going upwards. So let's look at the force acting on let's just take the system, okay? Let's do the system first. So for the system, the whole system is moving upwards, and so there's a net upward force. Okay, there's a net upward force. The forces that going upwards is the tension in this wire is upwards. Let's get this. So the force tension in the wire is going up because it is attached there, and it's pulling this mass up. Okay. This mass is attached to this thing, so it's gonna pull downwards. Okay. All right. Force going downwards as well is the force on this box. The force due to gravity is going to pull it downward. The force here, force due to gravity, is going to pull it downward. Right? Okay. So the mass of the system. So when you combine the top and the bottom box, when you combine the top and the bottom box, Um, all right, let's put it right here. So the mass of the system is 24.6 when you combine both of them, okay? 24.6. So that's the, okay? And so the force due to gravity for this, the force due to gravity is going to be downward for both boxes. And again, the force due to gravity is the mass times the acceleration due to gravity. Okay. Okay. So the force pulling downwards is on the system. So let's look at the system first, okay? The total force going downwards, all right? The total force going downwards is this weight and this weight, all right? Okay. And the force going upwards is the tension here, okay? All right. So again, we look at the system. Let's look at the system first, okay? If we because the acceleration of the elevator is gonna be, everything is gonna accelerate at the same rate because they're attached to each other. All right? Everything is attached to each other. So the net force, which is going upwards, is gonna cause the acceleration. Okay? So we know the force pulling upwards is is the tension right there, okay? And then the force pulling downwards is the weight, or force due to gravity. So the net force net, remember net force is what causes acceleration. The net force, let's call the tension here T1, all right, which is pulling everything upwards, okay? So this net force, which is T1, minus the force due to gravity of both of these things. And the force due to gravity is equal to the mass. So the combined mass is 24.6 times the acceleration due to gravity. And for simplicity, let's call that 10. Okay, so this net force is equal to T1 minus 246. So that's a net force. But we know that this net force gonna give the acceleration. And that net force, which is gonna give the acceleration, is equal to the mass of the system, 24.6, because that's the mass of the system, times the acceleration. And we know the acceleration, they gave us the acceleration. times 2.84. So 24.6 times 2.84. Let's see what that is. So that is 24.6 times 2.84. That is equal to 69.86. Call that 70. So let's call that 70. So the net force, and that net force, so the net force is upwards. We know that the net force on the system is 70, but that net force, as we say, is the tension minus 246. So if tension, all right, let's write it out. So tension, or T1, minus 246 is equal to 70. Then T1, that's a tension between the elevator ceiling and this box, is equal to, so you're going to take this 246 over here, so it's going to become positive. So that would be 246 plus 70, and that is equal, so 246 plus 70, that is equal to 316. So the tension in the top cable is 316. Okay, so this tension is 316. They also want you to look to find the tension in this, just this one alone. So you have to take this, you have to just look at this system. Just look at this alone. So what are the forces acting on the bottom box? The force acting on the bottom box is the weight force due to gravity in the bottom box. So the force due to gravity pulling the bottom box downward. Okay, force due to gravity pulling it downward. And then because it's pulling downward, there's a tension that's going to pull it upwards. So the tension pulling this upwards. Okay, so you just are going to look at this, just the bottom box alone. The force pulling it down gonna be the force due to gravity. The force pulling this upwards gonna be the tension. So call this T2. We don't know what that is. We don't know what T2 is. Okay? But we know the system is moving upwards, so we know that T2 is greater than the force due to gravity. The net force acting on this box gonna be the net force. So the force net acting on the bottom box is equal to T2, because its system is moving upwards, so T2 have to be greater than the force due to gravity. And then the force due to gravity in the bottom box, force due to gravity is the mass. The mass of the bottom box is 10.4, and then the acceleration due to gravity, we do just round it off to 10. So it's 10.4 times 10, which is 100 and 4. Okay, I hope I'm not moving too fast. Okay, so this is the net force, which is the tension pulling the box up, and the difference between the tension pulling the box up and the force of gravity pulling it downwards. The net force is going to cause acceleration. So this net force is which gives rise to the acceleration. And the acceleration of this small box is equal to its mass, which is 10.4, times the acceleration. And the acceleration of the system they gave us. Acceleration system is 2.84. Okay. All right. So the net force, which is T2, tension on the small box, minus the force due to gravity pulling downwards, that is equal to the mass, which is 10.4. So let's work that out. So that's 10.4 times the acceleration, which is 2.84, and that is equal to 29.53. Call that 30. So that's equal to 30. So T2 is tension between those two boxes. You take this over that side, so it becomes positive. So when you add them together, you get 134 newtons. Okay, so we solve for the tension between the elevator and the top box, and we solve for the tension between the top box and the bottom box. So, the important thing, everything is going to travel at the same speed or velocity. They're going to have the same acceleration. So once you get the acceleration for the system, you use the fact that the net force is going to give rise to that acceleration. The net force will give rise to that acceleration. And then you can use the acceleration that you calculate to look at tension, whatever else they ask you to do, you should be able to do it. All right. So let's all right. So we're gonna move on to another topic, and so we can solve some problems. So we've been looking at motion on a flat surface, but as you know that there are multiple inclined surfaces that you're driving on the road on a daily basis. You encounter inclined surfaces. You walk in, you encounter inclined surfaces. So you have to know how to manipulate what you have learned to assess motion on an inclined plane. And when we say an inclined plane, we talk about a tilted surface. So any tilted surface is an inclined plane. The rate at which object slides down an inclined plane is dependent upon the degree of tilt. So what we are saying, the greater the tilt, the greater the rate at which an object is going to slide down that inclined plane. So the greater the tilt, the faster the rate at which object slides. So, and this is just, it's an inclined surface. You put a load on an incline which has a certain angle with the horizontal, it's going to slide down. But why object slides? Why object slides? We're going to look at the physics of that, or the mathematics of that. Why object slides down an inclined surface, and then the greater the angle, the greater the rate at which it slides. So let's look at that. So what we're saying, if you have an incline, say 30 degrees, object is going to slide, a certain rate. Greater, say 45 degrees, it's going to slide down even faster. So the greater the incline, the greater the rate at which the object is going to slide down. And this is the reason why. When you have an object on an inclined surface, you're going to have a number of forces acting on the object. The force due to gravity is always straight down. The force due to gravity is straight down, downward. Okay? But the forces acting on this box is a force which is parallel to the surface of the incline. There's also another force which is perpendicular to the incline. And how we get those two forces is because if you look at the force due to gravity, so we have an inclined surface. The force due to gravity is pulling the object downward. But when you compare the force due to gravity to this inclined surface, it's not perpendicular. The force due to gravity is not perpendicular to the incline. Okay? So we can resolve the force due to gravity into two components. Okay? We can resolve the force due to gravity into two components. So we can resolve the force due to gravity, which is going straight downwards, into what we call a parallel component, parallel to the inclined surface. And then we can also resolve it into a perpendicular component, perpendicular to the incline. Okay? All we do is we use the force of gravity, and then we construct a 90 degrees triangle, making the force due to gravity the hypotenuse of that right angle triangle. And when you do that, okay, you construct a 90 degrees triangle, use the force due to gravity as the hypotenuse. Okay, the parallel component, which is the bottom portion of the right angle triangle, okay, or if you construct it up here, this parallel component of the force of gravity, remember the force of gravity is pulling downward, but when you resolve the force due to gravity, you're going to get a parallel component by just constructing the right angle triangle. It is this parallel component of gravity which is pulling the object downward. It's not due to the force of gravity. The force of gravity is pulling straight down. But the force of gravity can be resolved. You can break it up into two components. A portion that is parallel to the surface and a portion that is perpendicular to the surface by just constructing a right angle triangle using the force of gravity as the hypotenuse, and then you go parallel to the surface and then you come down. Okay, this is 90 degrees right here. Force due to gravity is the hypotenuse. Okay, this is the parallel component of gravity. and then this is the vertical, sorry, this is the perpendicular component, or you can use this, perpendicular to the surface. So when we talk about parallel and perpendicular, is to the surface, the inclined surface. Okay, so say for instance, this is, let me just, because this portion is very important. All right, say for instance, this angle is, say this is 30 degrees. This is, so this is an incline 30 degrees to the horizontal. Okay, if you come straight back, you get a right angle triangle because there's a force of gravity straight down. So this is a right angle triangle. So this is 90 degrees. So this would be 60 degrees, right? So this would be 60. This angle right here. Okay, but you know, this should be right on the surface. It's a little bit up, but this should be right on the surface. So if this is 60, this is going to be 30, right? 30 degrees. And of course, this is 90. So this is going to be 60. Okay? So the degree of inclination is the same as the degree between the force due to gravity and the perpendicular component. This angle is always the same as the angle of inclination. Okay? So if you have an object on an incline and you know the mass of the object, then you know the force due to gravity, and you can solve for the parallel component. It is this parallel component of gravity which is going to pull the object downwards. Okay? There is a component that is perpendicular to the surface and it goes straight up. The perpendicular component goes straight up, and this is this is the normal force now. On a flat surface, the normal force is equal and opposite to the force due to gravity. But on an inclined surface, the normal force is perpendicular to the inclined surface, and it's upward. So this would be the normal force. Okay? It's perpendicular to the surface. It is not straight up. It is not the same thing as the force due to gravity. That's only the case when it's on a flat surface. As a matter of fact, when you look at something, when you look in the dictionary and you say something is normal, it means it's perpendicular to the surface. That's what normal means. Okay? So you can use trigonometry equations to calculate the parallel component of the force due to gravity. Remember, it's this parallel component which is going to pull the object downwards. Okay? The force due to gravity is straight down, but because you have an inclined surface, you can resolve the force due to gravity into a parallel component and a perpendicular component. The perpendicular component is the normal force. The parallel component is pulling the object downwards. So if you use trigonometry principles, and we usually put, you know, this denotes that is the parallel component of the force of gravity. So that parallel component, wow, that parallel component, okay, because this angle is 30. If you remember your trigonometry function, the sine of this angle is equal to the opposite. This is the opposite over the hypotenuse. The sine of an angle is equal to the opposite side over the hypotenuse. This opposite side is the parallel component because these two are the same, right? Okay, so this is the parallel component, which is the same thing as this down there. So the sine, again, the sine of an angle is equal to the opposite side over the hypotenuse. So, all right, let me just write that out for you. The sine of an angle and so that's sine of the angle theta is equal to the opposite side over the hypotenuse. And this is a right angle triangle, okay? So the opposite side, this is the angle we're talking about. So this would be the adjacent side, this is the opposite side, and this is the hypotenuse. So the sine of that angle is the opposite over the hypotenuse. The opposite is the parallel component of the force due to gravity. And the hypotenuse is the force due to gravity. Right? Remember that the force due to gravity will resolve. But that's the hypotenuse. So if you're solving for the parallel component of an object on an inclined surface, that parallel component is going to equal to the force due to gravity. This is G, by the way. That's equal to the force due to gravity times the sine of the angle. So the parallel component, that is this component there, is equal to the force due to gravity times the sine of the angle of inclination, because this angle of inclination is the same as this angle right there. The normal force, so if you remember your trigonometry equation, okay, the cosine of this angle is the adjacent over the hypotenuse. So the cosine of an angle is equal to the adjacent side of the right angle triangle over the hypotenuse. Okay? So the adjacent, so this is the angle we're talking about. The adjacent side is the component that's perpendicular to the inclined surface. And we say that the component that's perpendicular to the inclined surface is the normal force. So it would be the normal force over the force due to gravity. So if you're solving for normal force an object on an inclined surface is equal to the force due to gravity times the cosine of the angle. You have to remember that. Cosine of the angle. Okay? So the parallel component of the force due to gravity is equal to the force due to gravity times the sine of the angle, inclination angle, and the normal force that an object on an incline is subjected to is equal to the force due to gravity times the cosine of the angle. All right, so you have to remember that, because that's going to come in very, very handy when we start doing problems, object on an incline. All right, so this is what we just draw. So again, force due to gravity is always straight down. But when you have an object on an inclined surface, there's a force that's pulling the object there's always a force pulling the object downward. And how you get that, you have to resolve the force due to gravity into its parallel component and its perpendicular component. It is this parallel component which is going to pull the object down. The perpendicular component, that's perpendicular to the incline, is the same thing as a normal force. Okay? So the force that pulling the object downward is the parallel component due to gravity. Remember what we said: when you have a net force, it is the net force which will give rise to acceleration. And because if this was flat, you wouldn't have any motion at all. But because it's inclined and you have a net force, the parallel component of the force due to gravity, which is pulling it downwards, this is a net force. And that is why when you have an object on an inclined surface, there's always a tendency for it to accelerate, because you have this unbalanced force, which is pulling it downwards, the parallel component of the force due to gravity. And this parallel component is equal to the force due to gravity times the sine of the angle of inclination. Okay? All right, so the parallel component is equal to the force due to gravity, which is mass times acceleration, times the sine of the angle. And the perpendicular component, which is also the normal force, is equal to the force due to gravity times the cosine of the angle. All right, we're going to leave it here tonight, and then the next time we meet, we will do problems related to incline. So you have some background information, so we will do problems related to that.